Whenever you write and run some code, you call a function, it does its thing, and then control just comes back. But have you ever stopped to think about what's actually happening under the hood? How does a program, maybe juggling thousands of function calls, always remember exactly where to return and what data it's allowed to see? Well, it's not magic, and today we're going to peek behind the curtain at the really elegant system that makes it all work.
I mean, think about it. It's such a fundamental question, we often just take the answer for granted, right? A function finishes, and boom, we're right back where we were, ready to go to the next line. But here's the thing, it's not magic at all. It is a beautifully organized system, and really getting a handle on it is key to understanding how our code actually comes to life.
Okay, so let's dive right in. The very first thing you've got to wrap your head around is that the call stack you might hear about in a language like Python or Java, well, it isn't the computer's main hardware-level stack. Nope. Interpreters, they kind of play by their own rules, and they build a completely separate world right there inside your computer's memory.
Think of it like this. The operating system gives the interpreter a hardware stack to manage its own business, the nitty-gritty of running itself. But for the code that we write, the code it's interpreting, for that, it creates a totally separate virtual stack. And this separation, this little walled garden, that's the secret sauce to the flexibility of these languages.
So if the interpreter is building its own stack, what exactly is it stacking? Well, the answer is this powerful little data structure that is, and I'm not exaggerating, the true hero of this entire process. It's called the activation record instance, or let's just call it an ARI for short.
Every single time a function gets called, the interpreter whips up a brand new ARI. You can think of this ARI as a self-contained capsule, a little bubble that holds everything about that one specific function call, its state, its data, and how it connects to the rest of the program. And when the function returns, poof, its ARI is popped right off the stack and destroyed. It's simple, super elegant, and incredibly effective.
To really appreciate just how powerful these ARIs are, we need to pop the hood and look inside. An ARI isn't just one thing. It's made up of several absolutely crucial pieces of information. So let's go ahead and dissect this thing and see what really makes it tick.
All right, first up, we've got the easy one, the return location. It's basically just a bookmark. If your code calls a function on, say, line 26, the ARI for that function call stores a little note that says, hey, when you're all done here, you need to go back and continue at line 27. This is how the program knows exactly where to pick up where it left off.
Next up is something called the dynamic link. This is a pointer, a little arrow, that connects an ARI to the ARI of the function that called it. It creates a chain of who called who. So if function A calls B, and then B calls C, the dynamic links form this perfect trail of breadcrumbs from C's ARI back to B's, and then from B's back to A's. This is the exact path the program follows when it's time to return.
Now hold on, because this is where things get really clever. The static link is totally different. It does not care about who called the function. It only cares about where the function was written in the source code. So if you nest function B inside of function A in your code, B's static link will always point to A's ARI. And why is that? It's so B has a way to find and use A's variables. This right here is the entire mechanism behind what we call lexical scope.
So let's just nail this down, because it's absolutely crucial. The dynamic link traces the path of execution. It's the runtime story of your program. The static link, on the other hand, traces the structure of your code, the lexical story. They answer two fundamentally different questions. Where do I return to versus where can I find my variables?
And finally, of course, the ARI is the container for all the actual data for the call. This is where it keeps any parameters that were passed in, all the local variables that get created inside the function, and even a little spot to hold the final result if it's a function that's supposed to return a value. It is the complete, self-contained workspace for that one function call. Okay, theory is great and all, but seeing this stuff in action is where it really clicks. So now we're going to walk through a piece of code that has a bunch of nested functions, and we're going to build the call stack, one ARI at a time. And I want you to pay super close attention to how the static and dynamic links behave, because they're not always the same.
All right, so our program kicks off, and an ARI for main2 gets pushed onto our empty stack. Simple enough. Then main2 calls a function named bigsub. So a new ARI for bigsub is created and pushed right on top. Its dynamic link points down to main2's ARI, because main2 called it. And since bigsub is written inside main2, its static link also points to main2's ARI. See? In this case, they point to the same place. So far, so simple. Next up, big sub calls sub 2. A new ARI gets pushed on top of the stack. And again, the pattern holds. The dynamic link points to the caller, which is big sub, and the static link points to its lexical parent, where it's written, which is also big sub. Our stack is now 3 levels deep. Everything is still straightforward.
And we keep going. Inside sub 2, we now call sub 3. What happens? You guessed it, another ARI gets pushed onto the stack. The ARI for sub 3 has its dynamic link pointing to sub 2, its caller, and its static link also pointing to sub 2, its lexical parent. Our little tower of ARIs is growing steadily. Okay, now this is the critical moment. This is what we've been building up to. Inside sub 3, we make a call to sub 1. So a new ARI for sub 1 is pushed to the very top. Now watch closely. Its dynamic link correctly points down to its caller, which is sub 3. Makes sense. But look at the static link. Whoa! Sub 1 is not written inside sub 3. If you look at the code, it's written way back inside big sub. So its static link doesn't point to the ARI right below it. It reaches all the way down the stack to point at big sub's ARI. This is the moment that reveals the true power of the static link.
So, why? Why go through all that trouble? Why does sub 1 need that special link that jumps down the stack to get to big sub? This is where we see the big payoff. This is the aha moment where the whole system proves just how brilliant it is.
Let's look at the code inside sub 1. It's trying to do some math. A equals B plus C. But wait a minute. If you look at the definition for sub 1, it only has its own local variables, A and D. It doesn't have a B or a C. So where on earth is it supposed to get them from? Without the right mechanism, this code would just fail. It would crash.
And this is the beautiful solution. First, the interpreter looks for B and C in sub 1's own little world, its local ARI. Nope, not there. So what does it do? It follows the static link. And that link doesn't go to sub 3. It takes a leap, jumping directly down the stack to the ARI for big sub. The interpreter then searches inside big sub's variables and, success! It finds B and C and can finally complete the operation. That right there is lexical scope in action, powered by the static link.
So, let's just boil this all down one more time. First, interpreters build their own virtual stack in memory. Second, every single function call gets its own little workspace, an activation record instance, or ARI. Third, the dynamic link follows the chain of calls, answering the question, who called me, so the program knows where to return. And finally, the static link follows the structure of the code, answering, where am I written, so functions can find the variables they need.
Isn't that incredible? This elegant, invisible dance of ARIs and dynamic and static links is happening millions of times a second inside pretty much every program we use. It's this powerful, hidden machinery that makes it all work. And it really makes you wonder, what other invisible engines are humming away under the hood, turning our simple lines of code into the complex, amazing software we use every single day?